All right, guys. In this series of videos, I'm just breaking down the most recent free response for AP Chemistry. Okay, so this is from May 5th, 2026. They released these last night. Um, and so the answers are out there. Um, so this is me just breaking down the test question by question. But I'm not just going for the answers in these videos because most of my students haven't taken the AP chemistry exam. They're taking it on the second date, May 20th, because we had another AP exam that conflicted with it. So um, most of my students haven't taken the test yet. So we're just kind of breaking this down and kind of looking at maybe different ways to approach questions. So not just what the clear cut answer choice might be or what College Board's expecting, but just kind of making a point to watch out for all the little tricks that they might play, the little details that you need to make sure that you catch to make questions. What might be a hard question turns out to be an easy question if you can kind of make those quick connections that we're always talking about. So we're going to start with question one. And remember, questions 1, 2, and 3 are going to be longer videos because there were 10 points. And then once we get to questions 4, 5, 6, and 7, probably shorter videos because they're only worth 4 points apiece. So not as much time spent on this. Okay. But so what I'm going to do is kind of take you through. So this is just the question. And then here's kind of like my annotations on, the question itself. And then we have the final answer, the answer key, and then we'll have our periodic table and formula sheet if we have to reference it, or just to make sure you know where to reference things and where to find things on the formula sheet. Okay, but so for question one, first thing, and again, you don't need to do this while you're taking the test, but know we know question one is worth 10 points. And if we count the number of prompts, we'll see that there's 10 different prompts. So like part A has 2. So 1, 2, 3, 4, 5, oops, 6 for D, 7, 8, 9, 10, right? So there's 10 different prompts. So that means if we have to say like we agree or something and then justify, we know we have to get both of those things right. Or we don't get the point. It's not 1 point for correct answer, 1 point for correct justification. So each one is worth 1 point. And we got to remember that when we're taking a test, right, maybe we know how to do part B, but it's just going to take a long time, or we're not sure how to do part B. We can't waste a lot of time trying to figure out how to do part B if we don't know what's going on. So we might want to cut and run and worry about these and don't get too bogged down on part B, number 1, because if you spend too much time here, 7B might be a really easy answer, a question to answer, and you're just not going to have that opportunity because you're not going to make it. So, right, it's about efficiency. You got 105 minutes. That's plenty of time. So you do have enough time to read everything, but you got to be effectively reading, right? You can't just like be looking at it. You got to, consume what you're reading and interpret it properly. So that might take a little time, and then you got to go. All right. So, whoops. Let's look at what I was saying. So for part A, they give us a potassium ion, and they make it easy. They remind us that the potassium in this compound is not neutral potassium; it's potassium 1 plus. They could have just said, what is the electron configuration of potassium in this compound? And you'd have to know that in that compound, it's not K neutral, it's K 1 plus. Okay. So what does that mean? It means we lost an electron. So it's normal electron configuration when it's neutral, but I've lost that electron. So now that's my electron configuration. Remember, it's going to be the same as its closest noble gas, which is argon. So it's going to be isoelectronic with argon and all that stuff. If we look at the key, right, a lot of students are just going to write the regular electron configuration for potassium. That's wrong. We got to write the electron configuration for argon because K plus is isoelectronic with argon. So that's your answer. And you don't need to write all this stuff. right? They just wanted the electron configuration. And so really all you needed to do was write that. Okay. So it shouldn't take much time, but you got to make sure. They could have done the same question and asked for chloride instead. And 1 minus means I gained 1 electron. So instead of being 3p5, which chlorine's electron configuration ends in 3p5, it would be 3p6, just like the potassium. So if they asked for the chloride would also have this same exact electron configuration because K plus and Cl minus are both isoelectronic with argon, right? Okay. So we go to the next one, and now this is just radius. We just, we need to know cations are smaller than neutral atoms, right? If I lose electrons, I get smaller. Now we got to explain it a little bit better. But my notes are, hey, cations get smaller, but we're going to have to explain it. So we know what the answer is, right? We know that K plus would have a smaller radius than K. We just have to be able to explain it, right? So we look at here, okay? We know that, neutral K would have a bigger radius than K plus, right? So again, my key is probably off here. So, right. Oh, it's saying what has a larger radius. So yes, so potassium would have a larger radius compared to K plus. Now I did mine in terms of how many energy levels they have, right? We're looking at their electron configuration. Potassium has 4 energy levels. Potassium 1 plus has 3 energy levels, but they have the same number of protons. So more protons, same number of protons, but less electrons is going to be able to pull those electrons closer to it, right? Right, but so that was my justification. I think that's good enough. You can talk about the proton to electron ratio. When you have the same number of protons, if you have less electrons, you're going to have a smaller radius. But, we're using atomic structure, and we're saying, hey, if my valence shell is n equals 4 and your valence shell is n equals 3, but we have the same positively charged nucleus, the one with less energy levels of electrons is going to have the smaller radius, right? All right. So we move on. All right. They give us some data. I note that here we got the molar heat of solution. So we're thinking calorimetry data. We have our initial and final temperature. As soon as I see that temperature went down, I know it's an endothermic process. If they ask me about delta H of the reaction, in this case, a salt dissolving in water, I know it's going to have to be reported as a positive value because it's endothermic. If temperature had gone up, then we know it's exothermic, and then I would have to report a negative value, right? Just all the things I'm thinking just when I see, temperature went down, right? Thinking calorimetry, probably thinking Q equals MCAT, right? But since we're mixing these two things together to make a solution, the mass that I plug into Q equals MCAT has to be the mass of the solution, which would be the mass of the water plus the salt that is dissolving in it. So you wouldn't use this as your mass number or just this as your mass number. You would have to add them for your mass number. Okay, so let's see how I annotated it. Okay, so I just said, hey, right, it wasn't we burned this much and then the heat from it went to the water. It was we added this to the water, so the solution has a combined mass of that, right? So something to think about. We know it's endothermic, and because temperature went down, remember we can only monitor the temperature of the surroundings, right? And that means the system gained energy as the surroundings lost energy, and that's an endothermic process. So delta H, when we report the delta H of the reaction, it's got to be positive, right? So those are all the things I'm thinking just by kind of a quick glance at the setup, right? So, where am I? Yep, all right. So part B was just telling us, how can we be sure of, let's go back to the worded question, how the student can use temperature readings during the experiment to determine the dissolution is complete. So because this was endothermic, right, think about what you would be doing in lab. You would mix them together and you'd be monitoring the temperature of the solution as the reaction is proceeding. And because it's endothermic, you would be looking for the lowest temperature reached, right? And so at the start, pretty much everything's room temperature. So the temperature of the room is probably 24.5. But then as the reaction pulls in energy from the water, the surrounding water in the solution, the temperature's going down, and it's going to keep going down until the reaction's done. So what are you looking for? You're looking for the lowest temperature reached, and then everything's going to start coming back to room temperature. If it was exothermic, you would be looking for the highest temperature reached before everything starts coming back down to room temperature, right? Does that make sense? So in my answer, I said, since this is an endothermic reaction, the student would have to monitor the temperature and look for the lowest temperature reached before the temperature started to come back up to room temperature. Okay. All right. Part C, calculate the magnitude Q in joules. So because our heat capacity down here was given to us in joules, we're just solving for Q equals MCAT. Magnitude just means we don't have to worry about the sign. But if we look to the next question, now we have to report the delta H with the proper sign. We already know the proper sign is positive, so we're good there. And if we just plug in the right data into Q equals MCAT, and we can just report the absolute value, we don't have to convert to kilojoules. So understand here, as I'm reading it, in part one, we're going to find joules, but in part two, we got to do kilojoules per mole with the correct sign. So, from part one to part two, we're going to have to divide by 1,000 to convert joules to kilojoules. And then what are we going to have to do? Divide by the moles. And we were lucky enough for them to tell us how many moles. But if we needed to, we would have to take the grams of potassium chloride and divide it by the molar mass of potassium chloride to get that mole number. But they gave it to us, so we just got to know what to do with it, right? So it's just Q equals MCAT. Remember, this 104.3 grams is the combined mass of the water and the salt. That's the heat capacity of the solution that was given to me. And then delta T is final minus initial. Now, so when we do Q equals MCAT correctly with the data, we get a negative sign. But remember, this represents the energy lost from the surroundings. So if we make it positive, that represents the heat gained by the reaction system, by the reaction. So the magnitude is just a positive 1,400 joules. The true data is a negative 14 joules. But again, that's the surroundings. And then in the next question, when we report the delta H of the reaction, we got to flip the sign to positive because it's an endothermic process. Okay. Let's check the annotations that I probably already knows. So lowest temperature reached, right? Q equals MCAT. Just a reminder here that the mass is not just this number or just that number. And then here we know it's got to be positive. Now, we're not getting a point for the right sign if we don't have the right value, because 10 prompts on question one, that's it. But we know it should be positive, right? So we got to take our joule value, divide it by 1,000 to make it kilojoules, and divide it by moles to make kilojoules per mole. Now, I'm realizing this as I go. We had two sig figs here, so technically I should make this just 15 and not 15.4. They didn't say for this question, make sure you have the right number of sig figs, so probably not going to lose a point there, but all right, you should always be mindful of sig figs. The instructions at the beginning tell you, but you really need to pay attention if they remind you in the question. And I don't think there was any question on this free response that said, watch out for the sig figs. So maybe if you wrote 15.4, you would get it wrong. Okay. And the other thing, I'm not expressing it a lot, but make sure, the only numbers that don't need units when you report them on the AP exam are going to be equilibrium constants and maybe like pH values, POH values, like you say pH equals a number, but like anything else, make sure you don't just report a number, report the units as well, right? All right, so okay. Part D, the calorimeter is not perfectly insulated, so we assumed perfect energy from the water to the system, but obviously some of the energy absorbed as the reaction proceeds is coming from, if it's a styrofoam cup, some of the energy is being absorbed from the styrofoam cup and not just the water. So what that means is, if we're not focusing on the energy that was added by the calorimeter and the rest of the environment that's close by, if we're not factoring that energy, then we undercalculated the the delta H of the solution, because it was actually pulling in more energy, but we only calculated the energy pulled from the water and not from the styrofoam cup or everything else, right? It's an easier, like I think if it's an exothermic process, it's an easier way to explain it, because not all the heat, the heat that was, if it was an exothermic reaction, if the heat released by the reaction is not just gained by the water, but it's also heating up the styrofoam cup as well, but you're only focusing on what's happening to the water, then you're going to undercalculate how much heat was actually released. So you're going to undercalculate your delta H of solution when you don't account for the heat capacity or the heat lost or gained by from or lost by the calorimeter or added to the calorimeter if it was an exothermic reaction. Hopefully that makes sense, right? But we know it's going to be less than, because we're not taking into account energy loss or energy gain from the environment itself. We're just thinking it's just happening between the water molecules and the ions, right? So let's see, it's going to be less than the sum of the heat gained by the system did not come only from the surrounding water. We are not taking the energy that was absorbed from the environment into account. So this value would be less than what it should be because we're not taking that heat into account. Okay. All right, part E. Okay. So a student performs a second experiment using the same mass of this compound. Now, we should know right off the bat, rubidium is heavier than potassium, but in case you didn't know, right, here's potassium, here's rubidium. Remember, the delta H is about energy per mole that reacts, not energy per gram. So it doesn't matter that we use the same mass. What matters is we're going to have less moles of rubidium chloride, because 6.8 grams of rubidium chloride is going to be less moles of rubidium chloride reacting, because rubidium chloride has a greater molar mass than potassium chloride. Okay. So where's my annotation here, right? Okay. So here I just said, oh, rubidium chloride has a higher molar mass. So if we use the same mass, we're actually using less moles. Okay. So is the magnitude of delta T when rubidium chloride dissolves, when that many grams of rubidium chloride dissolves, going to be greater than, less than, or equal to the KCl experiment? It's going to be less than, because less heat is going to be absorbed because less moles are going to react. Same amount of grams, but it's less moles, right? Let's see what I said on the key. I just did the calculation. I took the moles of KCl. Remember, it was already calculated for us, so I didn't have to calculate the molar mass of KCl, right? So if when that moles react, this is how much energy is going to be absorbed. In order to do this, I did have to calculate the molar mass of rubidium chloride, and if I do the stoichiometry there, only that much energy, right? So the rubidium is going to absorb that much energy, so the change in temperature is going to be less, right? Okay. All right. So part F. So let's take you on a tour of for my students, our chemistry units, right? So this is strictly unit 1 right here. Part A was strictly unit 1. Here we got calorimetry, so this is from our unit 3, right? Same with part D, so we got unit 3 calorimetry stuff. Part E is kind of like stoichiometry, calorimetry, just kind of a hodgepodge of units, probably 2 and 3 for us. And then now we have KSP, so unit 4, equilibrium and solubility product equilibrium, right? So they give us the equilibrium constant value at 28 degrees Celsius, okay? And so if we look at my annotation, the equilibrium constant at this temperature is greater than 1. We know that means the reaction is favored, so that means at that temperature, delta G would be negative. If they ask us about cell potential for some reason, that would be positive, right? So those are all things we kind of know just by, hey, that was the equilibrium constant value. It's greater than 1, right? They're probably not going to ask about cell potential for a salt dissolving in water, but maybe, you never know. So, just things to have in mind, Okay. Now, they ask us the molar solubility. So this would be awesome, if you review your KSP shortcuts, because this is a good time to do the shortcut so I don't have to make a rice chart, but making the rice chart won't take that long, right? And then here, if we read part 3, it's common ion effect. It's going to be less soluble in the presence of a common ion, right? So kind of boom, 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 just quick. And strictly, this is just 4-4 for us. This is not unit 4. This is unit 4, objective 4, right? So pretty quick to do, all right? So we have to first show the salt dissolving in water. Now, they didn't ask for states of matter, so I wouldn't put them if they don't ask for it. If they want the states of matter, they'll ask for them. But it's a salt dissolving in water. Now, they didn't remind us it was a reversible process. You should know, salts can dissolve. They can also precipitate if they're oversaturated. So maybe you need a double arrow here, but probably not. There's another question where they remind you, hey, this is a reversible process. And I bet you need to have the double arrow there in order to get credit. I'm not 100% sure, but you never know. But, this should be enough for a correct answer there. You do have to have the charge of the ions there. You could just have plus and minus. You don't have to have 1 plus. I always put 1 plus, but when it comes to minus, I always just put minus, but 1 plus, 1 minus, right? And if you wanted to include the states of matter, right? Solid ionic compound, aqueous ions, right? All right. Now let's talk about this one, the molar solubility, right? So what is molar solubility? It's how many moles of this compound will dissolve per liter of solution, okay? And so there's a couple ways to go about it. We can do it the long way where we're making a rice chart to figure it out. But if we're just dissolving in pure water, and that's what we're doing in part 2, KSP shortcuts, right? And it's the easiest shortcut, right? So let's go down the shortcut path. Rubidium chloride has a 1-to-1 ion ratio. So its KSP molar solubility shortcut would be KSP equals X squared, where X, and remember, College Board would say KSP equals S squared, where S represents the molar solubility. But remember, in these shortcuts, X represents the molar solubility when you're doing a KSP shortcut, right? So that's all we have to do. We know that KSP was 57, so the answer is just the square root of 57. But again, the KSP doesn't need a unit, but the molar solubility does. And what's the unit? Moles per liter, or capital M, molarity, right? Moles per liter, right? Now, where did the shortcut come from, right? If we forgot our shortcut, how do we get there? Well, we have to make a rice chart, right? So we have the solid dissolving water. We don't care about the amount of solid, but the rubidium is going to start at 0. The chloride is going to start at 0. We're going to gain 1 rubidium, and we're going to gain 1 chloride because it's a 1-to-1 ratio. So if I gain this X rubidium, I'm going to gain X chloride. So at equilibrium, right, rubidium and chloride are going to both be X. We know that the expression that KSP is equal to is this concentration times that concentration. So we plug in X and X, so we get X and X. We know the value of KSP is 57. Okay, so then we just take the square root of 57. All right, so notice we're doing the same thing, and it ends up being the square root of 57, so that's our answer. So to saturate the solution, it takes 7.5 moles of rubidium chloride to saturate 1 liter of solution, right? That's what molar solubility is. All right. So the last one here, they don't ask us to calculate the new molar solubility. We just have to know that it's going to be less when you try to dissolve a salt in the presence of a common ion, right? So we know the answer is less than, right? And what's the common ion? It's chloride, right? We're dissolving this salt, rubidium chloride, in a solution that already has chloride ions in it, potassium chloride. We don't really care about the potassium, but the fact that it already has chloride means it's not going to take as much of this to dissolve to get to the point of saturation for rubidium chloride. So if less dissolves, solubility decreases, right? Any measurement of solubility increases, even the molar solubility, right? So, and we just, I think we just have to invoke the common ion effect, and that's pretty much it. What do I have? Yeah, so common ion effect. All right. So we would say less than common ion effect. I would just shout out the common ion effect. And if you have time, this doesn't take that much to explain, but you say dissolving rubidium chloride into solution that already has chloride in solution will decrease the amount of rubidium chloride that has to dissolve before saturating, right? Something along those lines. All right. So that was question 1. Okay. Again, everything that I write down on this answer key is you don't have to write down to get full credit, right? You need to show your work. You need to have, words that explain the same thing or a calculation or something. But remember, this is more of a guide for my students that haven't taken this test yet. And, just things to watch out for, things to remember. Like, you didn't have to say isoelectronic for part A, but just remembering that vocab. Remember that we learned all that way back in unit 1. So it's been a while. So, make sure you're reviewing all that stuff. All right. All right. I'll catch you later for question 2.